It's always nice to have a whole pile of fossils to look at. This is a box of them that I was given by our friend Gary in Scotland from a famous historical site, and I've not had a proper look at them yet. So today I don't have time for much else, so what I'm going to do is have a good look at what's here and see what we can find. Hello again, everyone. This is going to be a slightly sort of shorter interim video than normal. Well, not sure about the shorter once I've done with it, but less editing intensive anyway. Because tomorrow I've got to go and introduce a possible sea slug to some electrons, and a few days after that we got someone coming here to talk about worms. So rather than leave you without anything to entertain you with for the next several days, I'm going to do a quick one on this where we look at some interesting fossils and see what we have. So this is from our friend Gary in Scotland. Hi Gary, thank you again. We have a little box of rabbit food apparently. Bunnies at lunch, yes, indeed. But it's also a box full of rocks. And this is, of course, the box of rabbit food that I like best. And it does include quite a lot of fossils. It's from a place called Neuk Quarry, or Mulloch Hill Quarry, in Ayrshire, Scotland. And this is an important historical site. It's from the Girvan district, which is one of the sort of classic areas of geology. And these particular rocks are from the Mulloch Hill group, which is late Ruthernian, which is early part of the early Silurian. So we're looking at rocks here that are about 440-ish million years old. And the second biggest mass extinction in history was at the end of the Ordovician at 444. So this is the aftermath of a major mass extinction event. And I'm really intrigued to see what the diversity is like, what there is here, and how the ecology might work, although you can't really get that too much from loose rocks. But, I mean, there's some very interesting things we've noticed just in passing, which is this is a sandstone. It's quite massive rock. There's a few sort of hammer marks on here. Somebody didn't get that one open, did they, Gary? But inside here, you can see there are fossils in cross-section. There are lots of little circular holes, bits of crinoids and bryozoans and stuff like that. We'll have a good look in a bit. Bits of shells and so on. But what's really interesting is that you have here a lens, effectively. It's a narrow region, well, it's about a couple of centimetres deep, which stops about here, goes around this side, stops about there. So it is a sort of a lump of extremely fossiliferous material in the middle of a less fossiliferous block. There are still fossils there. I can see a little brachiopod shell on the surface there. There's all sorts of little bits and pieces, the white bits on that side. But there's this really dense array of fossils in the middle, which we're probably going to have to very, very delicately sort of prise open in a way that doesn't damage anything and see if there's anything good in there. One or two blocks he's already split open for us, which is rather lovely. Yep, definitely split open. And the surfaces are quite prolifically interesting. So we have here all manner of little shells. Of course, I'll stick it under the microscope and we can have a proper look. But you can see straight away there's this weathering effect. So this is a calcareous sandstone. It's got quite a lot of calcium carbonate cement in it. And because of that, the shells are preserved intact, the calcite bits inside the rock where it's not weathered. So the white crystalline bits are calcite, which is the original shell material, probably a bit recrystallized, but it's the original material more or less. And then around the edges, it's been weathered. So this sort of brown stained mark is where the water has leached in around the side and dissolved the calcite away. So you have there all sorts of moulds which are often much easier to work with. From a paleontological perspective, you can quite often get better detail of many things like brachiopods and so on that you need the external form or the internal form, but the inner and outer surfaces. You need the surface detail to be able to identify them or interpret them properly. For those, you want these dissolved out bits so that you can just take a latex cast and mould it. For other things like bryozoans, though, you really need the internal structure of the skeleton. So something like these ones here, rather lovely bits of white stuff, that is what you want to study bryozoans. So, rocks are never quite accommodating for everyone who wants to look at them. And we have several blocks in here. There's another bit here of probably the same lens, I guess. Well, there's some different things in there. Yeah, intriguing. So there's plenty to have a look at. And I think to start with, we'll look at what's on the surfaces of that one especially, because that looks nice. Now, I just want to say before I start that this is not an area of rocks that I'm very familiar with. There was an ocean between Wales and Scotland at this time, or at least part of an ocean. I think the sort of Girvan group is kind of oceanic, somewhere in the middle with island arcs and stuff like that going on. But the main thing is that there are different species here than what we're familiar with in Wales. And in fact, we don't get a huge number of fossils in the early Silurian in Wales anyway. So there will be some similarities. I'll be able to make guesses, but I'm not going to know the exact species. I'm also kind of deliberately not looking up lots of stuff in advance because to some extent this is more about what we can discover, what we can work out from it, rather than trying to sort of remember details that someone worked out 50 years ago and trying to just label them. So this is more about exploring it than trying to just demonstrate my supreme knowledge or anything like that, because that's never going to work. So we have some rocks here. I've got this one underneath here. I have a torch for low angle light, should that be necessary. It probably will on one or two of those things. And we'll see what we've got. So I will start with something obvious, and let's go from there. So here we have a brachiopod shell. These are, well, I'll show you a brachiopod in a little bit, but they're bivalve shell. They have two valves, and they are still alive today, but they're relatively obscure. They're very unlike mollusks, which are, of course, abundant everywhere in pretty much any marine environment, and quite a lot of freshwater ones too. But the brachiopods, the lamp shells, actually dominated the sort of shelly fauna in the Paleozoic, particularly the Ordovician, Silurian. They were far more abundant than bivalves were. And so it's not at all surprising to find brachiopods here. And unlike most living bivalves, these things had a shell of calcite rather than aragonite, which means that it's more stable. They're both forms of calcium carbonate, but aragonite is more easily soluble, more easily recrystallized, and calcite is much more there for the long term, as long as nothing untoward happens to it. And if we zoom in on here, you can see that it's got a lovely original structure left. So there are thin layers. It's a laminar shell, which is entirely normal for a lot of these. And these are secreted gradually. They sort of add layers on the inside, which get gradually bigger as the shell and the animal grows. And better than that, we've actually got puncti. These tiny little pores running through the shell are very clearly in lines. They are structures that are part of the original structure of the shell. And you can see here there's a fibrous texture going through the material as well, sort of longitudinal fibers, and these tiny little pores in lines running along the ridges of the shell. And that is rather gorgeous. And this is probably the original, unaltered, effectively, calcite of that shell from 440 odd million years ago. And this has just been encased in a sandstone. It's been cemented by either calcite or possibly quartz or combination of the two. And that has basically encapsulated the shell and left it intact for all this time. So you've got really lovely preservation of the detail of the shell here. And that's just a very thin veneer. So that's the outer part of it. And even there we've got traces, sorry, the inner part of the shell. And even there you've got traces of this laminar sort of fabric, the lineations going along these ridges, some sort of fibrous structure internally, and those little lines of pores. So that is rather gorgeous. And it's when you see details like that that you think that, you know, things like bryozoans are perfectly identifiable, or they will be if you get them in a thin section and have a handy bryozoan expert on hand, which is probably the least likely part of that argument. Anyway, let's move on. What else we got? Let's go over this way. Something round. Yeah, I wouldn't like to say on that. It could well be a crinoid ossicle. So crinoids, as many of you at least will know, are these relatives of starfish and so on that have a long stalk, and the stalk breaks up into lots of little discs with a hole in the middle, polo mint type things, and they are composed of single crystals of calcite, which is why I'm thinking this is very likely a crinoid ossicle. Yeah, I'm sure it is. And because you can see that there is a similarity in the crystal form, the arrangement of these cleavage planes of the crystal are consistent across the whole thing. So that was probably a single crystal of calcite, and that's almost certainly going to be a crinoid ossicle. Not much you can do with that. That, however, is something different. That is a bit of bryozoan. I'll find you a better one because, yeah, that's not exactly great. Another crinoid ossicle. Oh, that's a nice one. Yeah, so as crinoid ossicles go, that's much better. You can now see the shape of the internal hole is sort of stellate. It's got points, quite a few points. Given these things are mostly pentaradially symmetric, you tend to expect that to be a pentagon in the middle, but that blatantly isn't. That is going to be a 6-pointed star, maybe even 7. Now, there are all sorts of different forms of crinoid ossicle, and I suspect that is a known one, especially because Gary's been working there and publishing quite a lot on crinoids, as it happens. So yeah, that's an interesting one. Normally you'd expect there to be only 5 points, but there's clearly going to be more, even though the left side of that lumen, as we call it, the central hole, is not at all clearly preserved. So there's definitely a crinoid. And you can actually look at the form of these ossicles to work out the diversity of crinoids that you've got. And they normally have, different species have recognisably different ossicle forms. And in fact, in the rocks around here, we had a friend of ours who moved away several years ago, but he was working largely on the Silurian crinoid ossicles of the area and was finding, I think we ended up with something like 30 odd species of crinoids in the offshore mudstones of the Silurian based on the ossicles alone. So there's a lot of scope to work with on those. Now there we go. Again, it's still in the unweathered part, the calcite preservation, and that is very clearly a bryozoan. Put the polarizer in. Oh yeah, that makes it stand out a little bit better. So what we've got here is something that, if this was in the Silurian of Wales or the borders, I'd be thinking of something like Tylodictyon, which is a bladed sort of form. So you have several longitudinal tubes that the animals lived in. This is a colony, remember. These tubes, called zooecia, is actually lying in one plane, effectively. There's a flat sheet composed of how many? 1, 2, 3, 4, 5. About 6 or 7 of these tubes lying next to each other. And the colony branches there. And I think you can see there's actually quite a lot of detail. Oh yeah, look at that. Really fine structural detail within the walls of these tubes. So we're not going to get any soft tissue in here. That just isn't plausible for this sort of environment and this sort of preservation. But we're getting really lovely preservation of the detail of the skeleton. And you can see the walls of the tubes themselves are made of little sort of almost cylinders stuck together. I think those might be what are called stiles, but don't quote me on that one. But there is a structure to the walls which gives you somewhere to work from when you're trying to actually do the taxonomy of these things. So I'm sure this is a named species. It's bound to be. And there will be a monograph out there somewhere that describes it. Nice. Okay, let's have a little more of a wander around. More crinoid ossicles. Let's have a quick look at them. Not so well preserved, these ones. That internal lumen, the hole in the middle, is difficult to work out what shape that is. And yeah, and here you can see we're going into the more weathered part, but there's another intact crinoid ossicle. Oh, that's rather nice. And there you can see these radiating ridges, which are the articulating facet, where the basically interlocking bits where these ossicles join together to form the stem. Actually only go through the outer half, and then there's a sort of ridge running halfway through the thickness of the ossicle on the left there, and then a great big round lumen in the middle. So that's a very different type of crinoid to the one that we saw earlier. And again, another bryozoan. This one is quite different. It's not a flat sheet, I don't think. Just take the polarizer out, see if that helps. Yeah, it looks much more complex. I think that's a three-dimensional array. You've got sort of overlapping of tubes on top of each other here. But the basic structure actually is very similar. No, I'm not convinced that is different. Maybe that's just a sort of branching point, and it's got a bit more complicated that way, but not totally sure on that one. It's a small piece anyway. And quite often you need to get a feel for the large-scale structure of these things just to immediately see whether it's the same or not. That's another one of the sort of branching Tillodiction-like things. Looks like another one next to it, I'd guess. Probably a bit thinner. Maybe that's a more distal branch. And ooh, hello. Okay, this is something we don't tend to get much around here. Right, I'm going to change the lighting on this one. So have that on your one side. Put the torch on. And now that is starting to leap out. This is a small fragment of something which is more or less flat. It's actually a domed surface. The centre is higher than the edges in this view. It's broken all around. This is just a small piece of something, which has a hexagonal, sort of almost honeycomb-like pattern on it. And this is a very distinctive thing once you know it. It's a calcareous alga. So we think of seaweeds as being soft and squidgy most of the time, but there are quite a few today which are calcitic. They have a calcite skeleton, which gives them quite a robust ability to be fossilized. And in the Silurian, there were a whole suite of things like mastopora, which have these sort of globose sort of forms with a skeleton of a thin sheet of calcite with this hexagonal series of ridges all over them. I'm not sure that we know exactly what it was like in 3D with the soft tissue and so on. I don't think anyone's got that good detail of preservation, but I think they're meant to be related to the Dasyclidales, the modern group. And this is a reasonably common fossil, I know, in some parts of Scotland in the Silurian. And you do get them in the Welsh borders, in the Whalenlock limestone, for example, but they tend to be a shallow water thing, mainly because, of course, they have to be in the photic zone. These are algae, so they photosynthesize, they need sunlight. That said, This is a small piece and it's on a surface that is covered by bits of debris, broken fragments of things. So who can tell? This may have been transported in from shallow water and it's been buried somewhere deeper. But in that case, there's a lot here that has been buried somewhat deeper. Okay, but that's rather lovely to see. You don't often get to see those where I'm from. And yeah, nice one to add to the collection. Let's see what else there is. So you'll notice that is iron stained and it's not white. So that's not because it wasn't originally calcite, it's because we're now getting to the edge where it is weathered. So it just crossed into the weathered zone, but right next to it actually is this bryozoan, which is preserved as calcite. And immediately next to it, that's dissolved. So that could be something to do with different amounts of magnesium within the skeletons. So calcium and magnesium are relatively similar sized and similar charged ions, so they can actually slot in to the crystal lattice. So you can get high magnesium calcite and low magnesium calcite. And echinoderms, for example, tend to be high magnesium. And high magnesium calcite is actually more soluble than low magnesium. So you may find that on a block like this, that you actually have a really clear difference between the preservation of different types of organisms that had slightly different crystallography or chemical composition of their mineral skeleton. And so we lose the skeleton in some, but we see it in others. But that said, this is very much on the edge of the weathered zone, so it might just be pure chance. I'm not honestly sure what Mastropora's skeleton was made of, apart from calcium carbonate. But we go this way towards the edge, and you can see it is very clearly just dissolved, and we're just seeing the outer moulds of these fossils now. So that is a bit of bryozoan. That's the outer surface, the impression of it, of the openings of various tubes. I would imagine that is quite a different bryozoan, but it's such a small fragment, it's hard to tell. We have... oh, we've got a trilobite. Oh, cute. So this is a very distinctive shape. We've got these big round middle lobe, and then the side lobes. Let me just rotate that actually, make it make more sense, hopefully. There we go. It's now a little trilobite that is the right way up. And so that is the axis in the middle, the right pleural region, basically the right side, and the left side. And those two arcs are curving downwards and covering the soft-bodied area, which would be where all the legs are underneath the protection of that exoskeleton. And normally when you see trilobite fossils, they're flattened because the rock is compressed and the fossil is probably flattened within the rock anyway. So they've probably been flattened before the sediment became lithified, and then the rock itself, the sediment gets compressed too. So you normally don't see the three-dimensional form, but when you have a rib in cross-section like this, that is the actual shape of the trilobite. You can see it's actually really quite tall. This is nearly as tall as it is wide, which is rather nice, really. You can imagine these being quite different to these sort of flattened, scuttly things that you might get the impression of them, things in mudstone, for example. So yeah, I would guess that is a caliminid, just from the robustness and the shape of it. It looks like a sort of caliminid, but I don't think it's really possible to be certain from these transverse views of a cross-section of a single rib. But we've got lots of other things here as well. Sitting underneath the shell is a crinoid ossicle. So this is now, of course, the external mould, and that solid bit in the middle is infilling the central hole, the lumen. And this is what I was saying earlier, a five-pointed star. That's the common type of lumen shape, or one of the common types. If you're going to have a star, normally it will have 5 points because crinoids are pentaradially symmetric. So you have that expressed through the lumen as well. And there's not much else to see there, but that is a tiny tiny little ossicle. It's about 1.5, 2 millimeters wide. No, it's less. That is less than a millimeter wide. That is a pretty tiddly little ossicle. Compared with something like that, which has a circular lumen and very fine ridges going over that articulating facet. I will use my torch again on that, see if I can highlight that a bit better. Yeah, you can hopefully see those little ridges a little bit more clearly now. And those ridges go all the way into the centre. It's almost sort of slightly angled lumen, maybe pentagonal-ish, but basically rounded. Okay, nice, nice. And once you start looking in detail, you find all sorts of other things going on. That's another crinoid ossicle with a very strong ridge halfway around the articulating facet. You got, ooh, what's that? Oh, a part of a large crinoid columnal, I think, there. Yeah, more bits of crinoid in different angles just stuck into the rock. And there seems to be a lot of bits of crinoid debris here. Bits of bryozoan, more bits of shells, brachiopods, bryozoan again. Oh, well, that's a nice bit of bryozoan. Yeah. So in this case, you can see the tubes are divided into short lengths, and those will be the apertures going out from the surface. So you've got your flat sheet, and the zooecia are basically coming out from the surface in sequence. So you've got a whole series of tube openings running up the sides of this sort of bladed structure. So it really does look like that particular bryozoan is actually quite a common thing here. And another rather nice little brachiopod shell there. This is actually away from the weathered margin again, so probably got the same sort of internal structure. Similar. Yeah, same species, I'd guess. You can see those lines of pores going through it. Yeah, okay. What happens if we go the other way? Lots more bits of the same sort of stuff. Yeah, bits of crinoid with different forms and structures again. It looks like it's got a definite little ridge around it and around the interior. Yeah, different species again. So there's a high diversity of crinoids here just based on the columnals, the bits of the column. And then there are bits of bryozoan and there are shells. But it is mostly a fairly low diversity assemblage, I think you could say. Little bits of trilobite as well. But that is a single bedding plane which has been winnowed. It has been concentrated on that layer, and so you wouldn't necessarily expect there to be a vast amount of variation within it, because these are all things that were living more or less in one area and then have been concentrated by mass, by size, and laid onto one plane. So not bad. Really lovely preservation of the calcite, and I'm intrigued by the sheer diversity. So I'm just trying to see. There are definitely, I think, probably 2 or 3 different types of bryozoan here, but mostly it's one species. We have one trilobite, we've got this one calcareous alga, we've got at least 1 or 2 species of brachiopod, but it's difficult to make out because we've only got partial shells of most of them. And yeah, so we're looking at a total of what? Including 4 or 5 crinoids, we're looking at 12, 13 species on that surface, which is interesting. Considering this is so recently after a mass extinction event, and a big one, it's, yeah, more than you might expect. Let's have a look what else there is. Before we go on to some other bits, I just wanted to show you a brachiopod. So this is a modern one. You can See, it's actually quite a pretty little thing. I'll put it under the microscope as well. And it has two shells, but they are different to bivalves. So what you have is this, the two shells are actually quite different. So in a bivalve, you have a left and a right shell. A bivalve mollusk, this is. And so you have a plane of symmetry between them, and each shell is asymmetric. In the brachiopods, it's actually a top and a bottom shell, so the plane of symmetry runs down through the middle of each shell. Each shell is symmetric, but the two shells are different. And in particular, one shell, the pedicle shell, has a hole in it, which is where a little muscular stalk comes out, and that attaches to a surface in most cases, or in a few groups actually is used to burrow. So there's only the one hole, that's in the pedicle shell. The other brachial shell is a little different. And yeah, they're just, other than that, they look a little bit superficially bivalve-like. But they are quite distantly related. The shells are independent as far as we know, although that's a really big, complicated issue, which we'll get to one day. But it's rather nice to see, and you can see that they're quite ornate structures. There are some colour patterns that have been preserved on brachiopod shells from the Paleozoic, which actually show sort of zigzag markings and things like that. So this would not be an unexpected type of colouring for one of these Paleozoic brachiopods, for example. And the other thing I want to point out is that this is a punctate shell. So those little puncti, the little tubes we saw running through the shell in the fossil, those are happening in lines. In this case, they're much less regular. We don't have the ridges that these little puncti are running along, but we've got the same structure. It's another punctate shell with little tiny little tubes running through the shell canals. So nice to see a living one in comparison. It's lost all the colour in the fossils, but the internal structure is still pretty much there. Right, something else then. There's a few little bits and pieces that are in this box, which include some peculiar things, I think. What did I see on this one? I did see something on it. Okay. Zoom out. There's just lots of little bits of bryozoan and stuff like that. Again, this is... Ooh, that's a bit weird. So you've got this sort of bobbly texture surface, which is absolutely typical for bryozoan. Those are the zooecia of a tiny tubed bryozoan. And then at the end, you've got much larger ones, which looks like something growing over the bryozoan. Either a larger one or more likely a small coral. That would be my guess on that one, but not enough there to be sure what's going on. Little bits of crinoid ossicle and more bryozoan. That's probably the same one that we were seeing elsewhere. So you've got these lines of tubes running parallel to each other and then side by side, and then the openings going outwards from the surface. We've got a little bit of a stem of a crinoid, where the stronger ridges are what we call nodals, which are slightly larger diameter, and then internodals between them. So if you saw this in end view, it would look like one of the crinoid ossicles that we saw before. It's a little chunk of the column with 1, 2, 3, 4, 5, 6, 7, 8, something like 10, 11 ossicles within that length. So that's nice to see. Oh, and there's one next to it. That's a single ossicle. And if you put that end on and stack a few together, you get one of those. Makes perfect sense, eh? But this is all familiar so far. But there was something else over here I thought was a little bit odd and wanted a closer look at. There we go. What's going on here? Right, okay. I think I know what's happening with this one. I'm going to need the torch again. Yeah. It's hard to be 100% sure because there are a couple of options. It could be the start of a tiny sort of coral colony with little tubes running out from a central bit. But I don't think so. I think this is a plate from the body of a crinoid, because the calyx, the body part, is covered in thin plates, which are often hexagonal, heptagonal, that sort of shape, and polygonal basically. And then some species have very strongly ridged plates, and I think that's what's going on here. That looks like a ridged plate to me. So, okay, not quite as different as I was expecting, but it's a different bit of probably one of the same crinoids, to be honest. In fact, you normally get those on a group called the camerates, which also tend to have nodals and internodals in their column, so that may well be a piece of the same crinoid as that little column that we were looking at. What's happened to me, light? Come on, light, be sensible. Somewhere else. Might well be that one, but hard to tell. You need a lot more. Ideally, you need a complete crinoid for that one. And then I'll have a look at this one as well, because this looks like it's got some nice bits in. And again, more crinoid columnals. And then these rather nice little bits of bryozoan. Again, these bladed ones, side by side, zooecia opening outwards onto the surfaces. But yeah, that's probably the same thing again. Just quite a lot of it. Lots. Oh, hello. Is that the holdfast? Oh, I think it must be. So you go from this end, which is absolutely normal arrangement of the zooecia, the tubes. That's exactly what we see elsewhere. You follow it down this way, it becomes narrower, and you lose tubes. It suddenly becomes more a single solid structure. And then it ends up like that, which has a smooth surface. There's no sign of individual zooecia there at all. And that, to me, looks like it is the holdfast of one of these things. So that was attaching to a surface. That might have been a soft surface, something like a seaweed. It might have been something hard, but there's no sign of it, of whatever it was attached to. So I think that is probably something attached to something soft, like a seaweed, like many bryozoans do today. And then it sort of came outwards, bent upwards into the water column, and then became this well-developed colony, which eventually splits at the top into two main branches. That's really rather nice. Oh, I like that. It's always really good to see something like the holdfast, because it tells you a lot more about what they were doing ecologically. And it also tells you this is quite a delicate structure, that this probably hasn't been washed around too far. It's very thin, it's made of calcite, so it's fairly brittle, and these things would snap if they're being washed around in a turbulent environment for significant lengths of time. So yeah, that is looking quite nice. I think there's one or two more bits over here as well. Same sort of thing. Bits of crinoid, bits of the same bryozoa. Yeah, nice, okay. Right, so that gives us a pretty good flavour of what a lot of this looks like. But I think we need to explore something slightly more, because geologists tend to be, kind of attached to their hammers, and they start getting twitchy if they haven't been able to do anything with it for a little while. And this is a nice big block here, which actually seems to have some cracks running through it. And there's nothing you can do if you've got a block with cracks in it. You've just got to wrap it up in a bit of bubble wrap to stop the bits flying everywhere. Otherwise the hoovering gets to be a pain. And very, very delicately and gently do that. And hope there is something in there. Oh, there is something in there. Okay, that's something unexpected. Right. Let's have a look at this one. Here we have something completely different. Isn't that lovely? That is very obviously a gastropod, a high-spired sea snail, and it is, well, there are some late Silurian ones in Wales that look very similar to this. Holopella, I think it is, something like that. But they tend to be, again, a shallow water species. These gastropods were almost entirely grazers, so they're living on algae. They need abundant algae in order to maintain their existence, really. So in order to keep themselves happy, they've got to be living in shallows. And let's have a look at the infill. As you can see, it's got this sort of rubbly texture inside where it's broken through. I think that is basically just grains of sand that have washed into the shell and gone all the way up. Yeah, so for whatever reason, the inside of the shell has not been cemented as well as the outside, which is just because probably a different microenvironment inside the shell, and so you end up with a you get the sediment washing in, but it's not stuck together in the same way as outside the shell is. So that's quite interesting. What else was there? Ah, yeah, there was also some of this stuff. Not immediately obvious, perhaps, at first glance, but we zoom in on here. I am hoping... Ooh, it's really poorly preserved. Bit crystallized. Recrystallized, rather. But I think this is, or I'm sure it is, a bit of bryozoan of a much smaller type. Lots of very small tubes within this. And this is probably a stick-like thing, which is basically a mass of tubes running up the centre of the stick and then sort of going outwards and all sides. So it's a much more complex internal structure in some ways, much more chaotic, certainly. And you have bits of the zooecia, the openings around the surfaces. So yeah, that's a little bryozoan, a different sort to the other one. Oh, what's that? Now that's intriguing. Let me just get two eyes on that one. Yeah, probably not that exciting. I think it's actually a flake of a shell in cross-section. I was hoping it might be something like a sponge spicule, but doesn't look like it. It's too sort of flat when you look inside in with both eyes, so you can see it in 3D. Right, okay, so that, apart from a few other little fragments of bryozoan and a couple of little shell fragments, is almost all that there was there. And one rather lovely crinoid ossicle. Look at that. Oh, isn't that gorgeous? And here we've got slightly curious preservation going on. You've got that little five-pointed star in the middle. The dark star is the lumen. The rest of it was made of calcite, and it has almost entirely dissolved away. So it's mostly an external mould with a little bit of rubbly calcite, which happens to be in the centre around the lumen, and so that would have been the centre of this mass of calcite. The weathering is eaten in from the outside, and it's just left that little bit in the middle, which is the pale area. So yeah, a little bit of the original calcite, almost eaten away. You can see that's very heavily etched, and yeah, there's not much of it left. But nice little star-shaped lumen there as well, and nice articulating facet. Looks like it's got nodals and internodals, so you've got the wider bit and the narrower bit. So yeah, you could do something with that if you were working on the crinoids from here. Another little fragment there. Lots and lots of little pieces. Okay, what else? What else? Right, I can see a plane through here which has lots of little bits on. tiny little sort of holes running down it. So I'm going to try to split it along that plane. Wish me luck. Now, a plane of fossils does tend to be a plane of weakness, so there is a reasonable chance that it will break at least partly along there, and you just got to sort of persuade it that it wants to, against its better nature. Okay, that has broken vertically through the rock. Fine. They never behave. That has also broken vertically, but through the end of it. Yeah, there are definitely little bits of rock in there. This is not doing what I want it to. But we can start to see... Oh, hang on. No, that is starting to split now. It's... Sometimes you just have to be a little bit more gentle when the cracks are starting to form. And hey presto. Okay. We haven't got the whole plane. We've just got a little bit of it has broken off. But it's a little bit of the right part of the plane. So we can at least see what's in there. See if it's anything different. Which way up is it? Tiny little fossils. Right, okay. And immediately you can see these iron oxide bits are fragments of fossil material. But this is not looking promising. You know what that is by now? One of those bryozoans, the Tillodiction type things. And we've got a different bit of bryozoan. There's a crinoid ossicle there. More bryozoan bits. This is not spectacular, is it? But that's what you get when you're out breaking things open live on camera. Bits of crinoid ossicle, bits of bryozoan. That seems to be the main part of this assemblage. I have got another slab here where we've got something on the surface. Definitely going to be worth a look at, this one. Yeah, okay. This is, ooh, it's too big. Ooh, right. Yeah, it's a slightly awkward shape in that this is on a surface, but the fossil is actually going into the rock, but it's conical, so that you can't see the overall shape of it. But what you can see very clearly is that there are sort of ridges running up the side, which consist of... Actually, it's a flat outer surface, and then there are ridges running inwards. So that's the shell of the structure in cross-section, where it has dissolved out because it was made of calcite. And you can see it's a very thin structure, and those blades pointing inwards are forming the ridges on the internal mould, but you don't get any ridges on the outside. It's just a little cup with little blades running inwards. And that immediately, to anyone who's familiar with the Paleozoic fossil record, tells you what it is. It's a coral. This is a rugose coral. It's a little solitary cup coral, and they are one of the two main groups of corals that you get in the Paleozoic, which were actually reef builders. So they were the equivalent of the modern scleractinians that we have today. They have a calcite rather than a aragonite skeleton, and they actually form moderately large reef structures. They tend to be what we call patch reefs rather than massive barrier reefs. But they can build up in little patches, and eventually you end up with a large structure like the much Wenlock limestone formation of the borders, where the bounding structures there are mainly corals and stratoporite sponges. So again, it's another confirmation that these things were living in shallow water, probably. They don't have to. There are some corals that live in deep water, but shallow water is most normal for this type of fossil. Okay. There was something else. Oh yeah, there was this slab here, which has got loads of stuff on that surface, and it's going to flake off the edge. So I'm going to just give it a little gentle bit of encouragement and see if it decides to actually behave itself. Probably won't, but you know, it ought to. Let's have a go. Trying to sort of tease it open by persuading it to carry on along the crack that's already there, which means you can't hit it too hard, and repeatedly is good. And it's getting somewhere. Well, it's not getting very far, but there are a few bits have just broken off. And in fact, the entire surface is now trying to break in half. So I might leave it there. I might also just try to prise this bit off with a little lever effect. That's going to take a little bit more work, probably out in the garden. But it's not bad. We've exposed something else different, so let's have a little look at what we've got here, because I think it's rather nice. Okay, we have a surface covered in large bryozoans. These are stick-like things. Yeah, unfortunately the whole rock is starting to come apart there, but there's a lot more that's still to be exposed, so it is going to be worth having a go at this. Yeah, stick-like bryozoans, mostly quite poorly preserved moulds, but there are areas where we can see where the holes were opening. The little... There we go. Yeah, I think what we've got here is sort of partial replacement by iron oxide, which really doesn't help. So the internal structure is kind of there, but very, very rubbly. So that's not great preservation, but there's obviously a lot of bryozoans on this bedding plane. And then over somewhere here, honest, I did see it. Where's it gone? Sometimes things vanish until you get the light at the right angle, and then something that's blindingly obvious, there we go, to the naked eye, becomes almost invisible. Right. That is quite nice, isn't it? That is the inside of one of these brachiopod shells. This is the brachial valve. It's the one without the sort of the hood sticking out that has the hole in where the pedicle comes out, the little stalk. So this is the other valve, and it's got this paired cardinal process there in the middle, and then grooves on either side, which is where the muscles are attached. I'll just use some low angle light on this again, see if we can bring out anything else. Yeah, not a huge amount there. It's all quite coarsely recrystallized, but yeah, it's worth seeing. So yeah, you've got a little bit of outlines of muscle platforms, muscle scars and so on, where the musculature was attached to open and close the shells. So it's just nice to see one of those. So that is a nice intact shell on a bedding plane covered by quite large bryozoans, which are mostly current aligned. Hopefully I can see that if I get on there. And you can see that these are all lined up. They are in mostly one direction, which is an indication that there was a current. So because these have hydrodynamics that are dependent on which orientation they're in, and they will tend to end up lined up with the current rather than against it. So when you see something like that, it's just telling you a little bit more about the environment that these things were being deposited in. And of course, that is one surface, and one can look for multiple surfaces in outcrop to see whether the ambient current was changing or not. If you tend to have burial by downslope transport, by things being washed out from shallow water under gravity, then you'll tend to get a consistent, or more or less consistent, current orientation. If it's something which is on the shelf in an area of wave activity at the mercy of weather and storms, then you'll tend to get different orientations. So you can actually work out quite a lot from details like that, as long as you actually have them in outcrop and therefore know what the current orientation is relative to each other. Or you can just get a single slab which shows current in either the same direction or different directions on different surfaces. But you have to get quite lucky for that. Right, I think that is most of what I can easily show you here. There's obviously a lot of material, but it's quite interesting looking at the total diversity because it's not enormously high, and yet it's got all of the major groups you would expect. So we've seen only, one species of trilobite from a rib. Actually saw a couple of ribs in the end. Maybe 2 brachiopods, maybe only 1. It's hard to be sure without better, without more parts and counterparts, so you can match up the internal with the external molds and make sure that you're looking at the same thing, because the inside and the outside of a brachiopod shell can look completely different. The pedicle and brachial valves can look completely different. So you can have 4 different shells that you're trying to correlate to one species. So that would take a bit more work to be sure that we're looking at just one species of brachiopod, or maybe 2 or 3, but it's not that many. Bryozoans, 1, 2, probably 3 or 4 bryozoans. I would guess 4 or 5 crinoid columnals based on a species based on the columnals that we've seen, and then I think there's probably a couple of corals there, and 1 calcareous alga. And I think that's about it. Now, obviously, that is not going to be the total diversity of the site. It just isn't anything like the total diversity because we're not seeing soft-bodied animals. We're not seeing the really delicate things preserved intact. We're just seeing a scattering of things that were preserved on these surfaces. And I imagine what we're looking at there, 15 odd species. If we were to actually sit there like Gary does and keep hammering and trying to work out the total diversity, I imagine the total diversity is going to be between 50 and 100 species, probably quite easily. It may be more, but I would guess 50 to 100 is what the diversity at that quarry is likely to be in the region of. Mainly because this is at the age that it is. So if we were looking in the Wenlock limestone formation, kind of similar, but a limestone rather than a sandstone, and with a lot more sort of exceptional preservation. But if we were looking there, we might expect with long-term work to get up to a few hundred species. It's got very high diversity of things like brachiopods. I think there's 60 species of trilobites, 50 crinoids, similar numbers, 30 or 40 bryozoans, and so on. It just keeps going. And there will be lots and lots of rare species here as well, because the nature of a hollow curve is that in a box this size, we're going to be mostly seeing the common things. And when you actually spend years there, then you start finding the rarer things as well. But this is from very shortly after the end Ordovician mass extinction, when 85% odd of species disappeared. Unlike most of the big mass extinctions, though, the end Ordovician was peculiar in that ecology recovered remarkably quickly. This looks like the same type of fauna as you would get in a late Ordovician shallow water reef type environment. It's got the same sort of mix of major groups, the brachiopods, the crinoids, the bryozoans. You would see this in similar rocks that we have in South Wales, for example, in the Sandbian Cation, where you get, again, quite a high diversity of things. Well, actually, you get reasonable preservation, where you get, in that case, exceptional preservation of echinoderms all over the place, loads and loads of bryozoans, and you can get, in total, a very high diversity there. So it looks like we've got a sort of cut down version of the ecosystem in the early Silurian, and this is what we tend to see worldwide, that very rapidly we get the same sort of ecology building back up. We have your little coral reefs, patch reefs, we have bryozoan thickets, we have crinoids multiplying, but we don't yet have the high diversity. That takes longer to build up, but in the early Silurian we do have the basis of that diversity reforming again. And there's big questions over why the end Ordovician didn't radically change the ecology of these shallow water communities. In the deep water, it does seem to have had a major difference. There are various groups of deeper water trilobites, for example, that basically vanish. And in the deeper water Silurian, we just don't get the diversity and abundance of trilobites that we see in the Ordovician. So it does look like on the offshore environments there was a big change, mainly probably because the anoxia out there was pretty pervasive and, yeah, wasn't a good time. But in the shallow water, anoxia is not so much of a problem. You just knock out a lot of species just because of general knock-on effects of ecological crises, and you've still got enough of each group there that they can repopulate and rebuild basically the same ecology. So I think that's what we're looking at here, is a low diversity, at least at first glance. It's dominated by the same species turning up again and again in a way that is much more obvious here than in the late Ordovician rocks that we've seen down here. But it's a low diversity-ish fauna. It's still not bad, but it's not as high as you'd expect later in the Silurian, which is nonetheless quite happy. It's kind of thriving. It's obviously got very high abundance. You obviously have some ecological subdivisions going on. We've got these bryozoans which have different species dominant on different bedding surfaces, maybe because of hydrodynamic effects and winnowing, but more likely there's some ecological difference going on. You've got some things which are living in thickets together, and then there are others which are possibly living more commonly but scattered around. We've got diversity of crinoids, but you'd need to be like Gary and spend ages there actually working on the crinoids to work out how many species there are and what their ecology was like. So in Llantegli rocks and a shallow water fauna from the Middle Ordovician around here, we do have very obviously different ecology. So there's one type of crinoid that only lives apparently in dense clusters, where it's sort of building up and living on the remains of the previous generations. And then most of the other ones are single specimens. So there's a lot of diversity in life habits and ecology of even things like sea lilies. Anyway, that was fun. Hope you enjoyed that as much as I did. Thank you again to Gary. That was lovely. And I will be back with probably one of the more sort of detailed discussion things coming up. Might be early next week now because we're just so tied up for most of the rest of the week, but I'll be back soonish, before you know it, honest. Thank you again for staying till the end, and if you would like to support the channel, we do have membership where you get extra videos, 2 or 3 a month, something like that, based on unpublished work that we're doing mainly on the Castle Bank biota, where we have soft tissue preservation of weird stuff. No obligation to do that at all, of course, but stick around, like, subscribe, all that sort of stuff, and we'll hopefully see you again. Bye for now.